you're probably already familiar with, but there's going to be some stuff in here that's going to be new to you as well. All right. We've got about 40 minutes left before we break for lunch, so I don't think we'll finish this chapter, but we'll get through a good portion of it before that break. So in chapter 3, we're going to talk about securing the layer 2 infrastructure. Excuse me, when we talk about securing layer 2, obviously we're talking about securing the LAN, securing their switching environment. All right, and there are actually a lot of vulnerabilities that show up in the switching environment. Let me demonstrate something to you guys real quick, and to give you an idea of what some of these vulnerabilities might look like. I'm just going to use Packet Tracer here, and I'll drop in a 2960 switch and a couple of PCs. All right, and we'll just connect all these devices together. And I'll go into this switch, and we'll say that this is basically my production LAN, right? So I'll go into this switch here, and I'll just call this switch corporate. And we're going to create VLAN 100. We'll create, give that a name of data 1, and then we'll create VLAN 200, give that a name of data 2. And interface, I forgot which ones I plugged those into, so let me do this. I'll put the PC on the left into port 1, and I'll put the PC at the bottom here in port 2. And what I'll do is I'll go ahead and go into interface FA01, switch port mode access, switch port access VLAN 100. So we're going to go through this again in the chapter, but I'm just assigning a VLAN to that particular port. And then I'm going to go into interface FA02, switch port mode access, switch port access VLAN 200. All right. And I will even come in here and I'll say enable secret Cisco line VTY04 password Cisco login. So I'm securing access to the platform, right? Now Cisco is obviously not a good password, but I'm trying to demonstrate something that's very important here. So I've got my corporate network, it's running, this PC is connected, this PC is connected, everything is working great. All right. These are switch interfaces. Switch interfaces are turned on by default, so we don't have to do the no shut on the switch interfaces. Now what I'm going to demonstrate here is actually a real vulnerability. If you have Cisco switches in your network and you go do your VLANs, you configure everything. I even went as far as setting it up so that my host ports were pretty well protected. But let's say that I'm an attacker and I am interested in obtaining your VLAN database, right? I'm an attacker and I'm interested in obtaining your VLAN database. So I bring my little switch to your office, which is my attacker switch. We'll call this hostname attacker. All right, so you can tell the difference. So I've got my little attacker switch. I'm going to go into interface FA01, and I'm just going to say switch port mode trump. Literally one command. That's all I'm going to put in that switch. And then I'm going to take the attacker switch, and I'm going to plug my attacker switch into your switch. So take port 1, plug it into port 15 or 14 or whatever it is. All right. Now, I'll wait for spanning tree to do its thing, let that port come up. It'll take about 50 seconds. But in the meantime, I'm going to go ahead and also show you the VLAN database on the attacker switch. Show VLAN. And on the attacker switch here, I can see that, let's do that again. I've got the default VLAN. That's it. Now remember, all I've done is plug my switch into yours. on a port with a default configuration. Config T, VTP, domain, hack you. All right, and show VLAN. And now I have a copy of your VLAN database. Never logged into your switch. Never authenticated to your switch. Just changed my domain, my VTP domain name to hack you, and I got a copy of your entire VLAN database. Okay? Now I've decided, all right, now I've got a copy of your VLAN database. By the way, now I can do a VLAN hopping attack. I can do denial of service attacks across the VLAN because this is a trunk passing traffic for multiple VLANs, right? But what's worse is I can go ahead and shut down port 1, interface FA01, shut that down, and I can say no VLAN. Well, actually, technically, I don't even really need to shut it down, but if I want to be very dramatic, I can shut it down, right? No VLAN 100, no VLAN 200, all right? Interface FA01, no shut. Let's do spanning tree port fast as well so that it comes up quickly. Look what happened to the 2 ports on the production switch. If I go into my production switch, show VLAN, VLAN 100 and VLAN 200 are gone. So not only did I get a copy of your VLAN database, I deleted your entire VLAN database. And all the hosts that are a member of those VLANs, their ports are now error disabled. That's why they're orange right now. And I can even push out VLANs. I can say VLAN 666 name, hack you. And if I go over to this switch, I do a show VLAN. And I can see VLAN 6666 is now, or 666 is now in your switch, right? And I've done all of this without even authenticating to your switch. This is the default behavior. There's 2 protocols that are at work here, DTP and VTP, the VLAN trunking protocol and the dynamic trunking protocol. All right. Now Cisco obviously over time has realized this, so some of their default configurations are starting to change so that you're not vulnerable to these types of attacks. But these are layer 2 attacks that can exist. If you got 2960 switches running 12 code, you're vulnerable, right? So obviously when I teach the VLAN component of CCNA, we talk a lot about how to avoid these types of vulnerabilities. And we're going to see that again in this chapter. There's other types of attacks, though, that can occur. All right? So the goal of this chapter is to kind of go through those concepts. From Cisco's perspective, and I think it's a good perspective, hardening the foundation is more important than hardening the application. Because if your network foundation isn't secure, having all the security in your applications is not going to help, right? Especially when it comes to denial of service. Can you imagine the result of somebody doing that in your enterprise where you have a 6513 or you have multiple switches trunked together? Because, by the way, that VLAN propagation would occur across your entire network. Every port in your enterprise error disabling. Imagine the chaos that would ensue in that environment, right? So obviously there are some very simple techniques that you can use to protect against that, but some people forget to do them, all right? So unless the foundation is secure, how can the rest of the network be secure? All right? Unless the foundation is secure, how can the rest of the network be secure? Here's another example. I used to own a service provider company. It's small, excuse me, small ISP. We did dial-up. This was back in the day when dial-up was a thing, and we did T1s and stuff like that. But our equipment was housed in a data center, like a co-location facility. And I won't mention the company, but it was Quest. But their racks were not fully enclosed racks. They were lockable cabinets, but they had slits in them for airflow. The doors had slits in them, not perforated doors, but slits. And one of our neighboring folks, they weren't part of us, but they were there. The guy was there, and he said, "Man, somebody came in and stole all our SFPs because that switch just happened to be right in front of one of those slots where you could put your fingers through, and they just pulled out all the SFPs because those things are like gold, right? They cost like $1,000 a piece." So that's kind of a denial of service attack, isn't it? I mean, essentially, we just brought down your whole network because we pulled out all your physical layer components and stole your SFPs, right? So unless you're protecting the infrastructure, protecting the application is kind of pointless. So we're going to kind of look at network protection following this protocol stack, going from the physical layer up to the data link layer and so on, although we don't spend as much time talking about the physical layer. In fact, we're going to start by protecting compromise against the data link layer here. All right. So how does a switch work? All right. Well, since we're recording this for YouTube and they don't have the benefit of having gone through the CCNA class, let's just do a quick review, right? Switches, first of all, are passive devices. They have essentially no security in them whatsoever initially. They have no protection mechanisms in them. They trust essentially everything they're told, right? And what they do is they simply monitor frames as they go back and forth. As frames move back and forth from one port to the other, the switch builds a database called a MAC address database, or a content addressable memory database, right? A CAM table. What goes into that database? Right. What we're learning about the hosts that are either attached directly to that switch or hosts that are communicating through that switch, right? If I come into my network here, let's get rid of our attacker because we found him and we shot him, all right? And let me add my VLANs back here. Config T, VLAN 100, VLAN 200. I'm going to go ahead and put both hosts in the same VLAN so we don't have to do routing. Switch port access VLAN 100. And let me just put a couple of IP addresses on these PCs. 10.10.10.1 and 10.10.10.2. All right. And I'm just going to do a quick ping, 10.10.10.1. All right. Now, spanning tree is still doing its thing, but eventually it'll be done. And then we can actually see the pings go through. Now, the switch hasn't been configured for anything but VLANs, but it's monitoring this traffic flow. And it's building something called a MAC address table, do show MAC, dash address. And this MAC address table is a very simple database that stores MAC address to port number. But and additionally, it also stores the VLAN information. That's very important because that is something we're going to talk about later on when we talk about private VLANs and how private VLANs help us add additional level of security. Something you guys, though you've probably dealt with VLANs on a regular basis, private VLANs is probably something you haven't seen before. So that'll be interesting in this chapter. But the switch is building this database, right? Now, I'm somewhat limited with Packet Tracer on showing you certain things, but if I do a show VTP status, which doesn't really technically have anything to do with VLANs, it's a way for us to propagate our VLAN database, but it does tell me one thing. Well, it doesn't really tell me that, actually. I thought it would. Packet Tracer doesn't show us that. Show VLAN, let's see, what does it give us? We don't really get a whole lot, right? There's some commands, and that's what I wanted to demonstrate. There's a command that you can run to identify essentially how large that database can become, right? there's a specific set of memory that's allocated in a switch to store MAC address information. And some switches, you can change how much memory is being allocated for that process, right? There's a way to switch the function of a switch by changing its footprint. Is this a multi-layer switch that's primarily used for routing, or is it a layer 2 switch that's primarily used for switching? But the bottom line is this MAC address table is finite in size. Let me generate some more traffic. This MAC address table is finite in size, meaning that only so many entries can go into that table. We'll talk about why that's important here in a couple minutes. Switches use this database to make their forwarding decisions. There's two things that a switch will do with a frame. What are they? Forward it or flood it. Right. A switch will either forward a frame or it will flood a frame. If the destination MAC address is not in the database, the frame gets flooded. If the destination MAC address is in the database, the frame gets forwarded. Now, we're talking about this from the perspective of security. From an attacker's perspective, is it better for a switch to flood frames or is it better for a switch to forward frames? Flood. Right, because I want to be able to capture those frames. If I'm an attacker sitting off on this port and the switch has learned everything, data that goes from that PC to that PC or that PC to that PC or this PC over to this PC, I'll never see it. All I'll see is broadcast traffic, or I'll see maybe some unbounded multicast traffic if we're not running things like IGMP snooping. So the goal of an attacker in this environment is to try to make the switch flood data as opposed to forward data. And we do that by initiating something called a CAM overflow attack, or some people call it a MAC flooding attack, where I simply inject or send in a whole bunch of bogus frames on a port with the goal of filling up the MAC address table with that bogus information. Now, if you think about the concept, if I'm the attacker, I kind of have to do that before the switch learns information, right? So it's not as simple as it sounds, because these hosts most likely are probably already been communicating for a while, right? What happens when the MAC address table gets full? Well, it doesn't flood everything. It floods everything that's not known, right? But if the MAC address, let's just say, assuming in a perfect attacker's world, I was able to get access to that switch before anybody else. So I flooded in thousands and thousands of bogus MAC address, bogus frames to fill up the CAM table. Now this PC talks to this PC. The CAM table is full. Do the frames get propagated? Yes. Just because the switch doesn't know how to get to a destination doesn't mean it drops the frame. What's going to happen is this PC's MAC address is not going to end up in the database like it normally would. So now the response gets flooded. Any traffic to that PC gets flooded. And that is a CAM overflow attack. We'll see that again in a couple of slides here. Another concept of a switch is what we call a VLAN. A VLAN is a logical broadcast domain within a physical device. All right, so if I have a switch here and I have PCs connected to this switch, by default, every one of those PCs is in VLAN 1. And VLAN 1 is what we call an untagged VLAN. All right, it's our default native VLAN. It doesn't always have to be our native VLAN, but by default, it is the native VLAN. All right, so if this PC is, let's say that this is the 10.10.10.0 subnet. This PC is .10, this PC is .11, this PC is .12, that PC is .13. They're all in VLAN 1. All right, which creates this logical broadcast domain within VLAN 1. But let's say that I go ahead and I take this PC here And instead of having it in VLAN 1, I'll just use a different color to represent a different VLAN. I put it in VLAN 10. Now, I didn't change its IP address. I didn't change anything about the configuration, excuse me, on the host. But what I've done is essentially isolated that host from the rest of the other hosts. How did that happen? Remember, that host is still in the same subnet as the other hosts, right? But when the traffic comes from this PC, it gets tagged. It gets tagged at the switch port into a VLAN because the port itself is a member of that VLAN. We don't make a host the member of the VLAN. We make the interface a member of the VLAN. So there's a tag that's applied to the frame for VLAN 10. Remember that MAC address table that we talked about? And we see that here, that the tag that was applied was 100. By definition, the switch is now only allowed to forward that frame to other hosts within that VLAN. All right, I lost my little switch here, but let's go ahead and put it back. So essentially what I've done is I've taken this switch, I don't want to use that color. I've taken this switch, oh, come on. I've taken this switch and I've logically divided that switch up into two separate switches. And we've got some hosts over here in VLAN 1. We've got a host over here in VLAN 10. By definition, that switch is not allowed to forward those frames to any other host except for one in VLAN 10. So how do I get from one VLAN to another? Router. You got to go through a router or a routing process. Right. All right. So this VLAN concept allows us to logically separate the traffic flows in our switch. So another type of attack that an attacker will try to use is what we call a VLAN hopping attack. All right, a VLAN hopping attack, where I try to manipulate the tags or I try to gain access to a trunk or whatever it is so that I can start to insert frames on multiple VLANs. We're going to see the different attacks after lunch and how we can mitigate those attacks later on. All right. All right, so let's just see what it says on here. A VLAN is a logical broadcast domain. It provides segmentation. Ports in VLANs share broadcast domains. Ports in different VLANs do not share broadcasts. The reason that is true is for twofold. Number one, because of the tag that gets applied to the frame. And number two, because the switch is designed not to forward frames from one VLAN to another. All right? So by putting in VLANs on a switch, now all of a sudden, you're forcing that inter-VLAN traffic to have to go through a router or a routing process, like multi-layer switch SDIs. All right? Also, in order to pass traffic from one VLAN, or excuse me, from one switch to another, we're still within the VLAN, but from one switch to another, we use this thing called a trunk. All right. Now, by definition, a trunk is any interface that has to carry traffic from more than one VLAN. Most people think switch-to-switch links are trunks. And in a lot of cases, that's true. But it doesn't have to be. What else is very common in a network where we would see a trunk? Switch to router if we're doing router on a stick, right? Or VMware servers, right? VMware servers have multiple ESXi hosts on them, and they have a virtual switch internally, and they do tagging and all that, all right? Now, a trunk is not a layer 3 entity. It does not allow us to pass traffic from one VLAN to another. So in other words, I can't go from this host in the data VLAN over to this host in the management VLAN over that trunk. think of the trunk as kind of like these different tunnels to pass this different VLAN traffic, right? The data VLAN tunnel, the management VLAN tunnel, the voice VLAN tunnel, but you can't go from one tunnel to the other. That attack that I demonstrated when we started this chapter took advantage of creating a trunk dynamically. I mean, I literally only had to do one command on my switch to be able to gain access to your switch without ever authenticating. All right. So how do we configure VLANs? Well, there's actually 3 steps to configuring a VLAN. All right, 3 steps to configuring a VLAN. The first step would be to create the VLAN in your VLAN database. And that's very simple. If you want to create VLAN 10, you type VLAN 10. If you want to get rid of VLAN 10, you type no VLAN 10. And you give it a name, right? If you want. The name is kind of for you only. Doesn't really have a whole lot of relevance. It's not carried in the frame. All right. The second step would be to assign your VLANs to your interfaces. All right. Now this is where people make a mistake. This is where people make a mistake because technically the only command that you need to assign a VLAN to an interface is that command right there. Switch port access VLAN 2. All right, let me demonstrate. I've got VLAN 100 on my switch. I'm going to go into port 3. Config T interface FA03. And I'm going to say switch port access VLAN 200. All right. And I'll just plug a PC in there. Let me just move one of these. Let me just do a separate PC. So I'm going to put in this separate PC here. I'm not going to configure it. We're not going to use it. But I want to show you something about this configuration. Now, technically, that port is in VLAN 200. All I did, I had already created the VLAN when we did that exercise before. But all I did was assign the VLAN to the interface. If I do a show VLAN, I can see that port 3 is now a member of VLAN 200. I did not do the switch port mode access command. If I type show, let me get out of config mode, show interface FA, show interface switch port, okay, and I go down to my fast Ethernet 03 interface, we can see from this output that in fact the port is in VLAN 200. Great. But this is the key right here. This is the key. The administrative mode of that port is dynamic auto. Now it's presently operating as an access port, meaning that a host is connected to it in a single VLAN. But that port is running in dynamic auto mode. Does anybody know what that means? What dynamic auto means? DTP is enabled on the interface. The dynamic trunking protocol, which is a proprietary Cisco protocol that's used to negotiate trunk lengths, is enabled on that port. So if I'm an attacker, guess what I can do? Unplug my PC, plug my switch in, send DTP, the port becomes a trunk. Now I can start attacking other VLANs. Or I can steal your VLAN database, whatever. There's a lot of things I can do. So people will do their VLAN configurations. They'll assign the VLANs to the ports, but they won't disable DTP. That's what this command does right here. That command technically disables DTP. So as a best practice standard, that's something that you need to implement. Okay? If you don't, you're vulnerable to VLAN hopping attacks. If you don't, you're vulnerable to many other things like stealing the VLAN database through the use of VTP and so on. See, if you notice, I did switch port mode access on my other ports. Notice that the administrative mode is not dynamic auto. it is static access. And you can even see negotiation of trunking is turned off. Whereas if I go down here, I can see negotiation of trunking right here is turned on. It's such a simple configuration. I always ask my students, hey, what is switch port mode access? And I always get the same answer. It makes that port an access port. But they don't understand the implications of DTP. The port will become an access port with that command or without it, as long as DTP messages aren't being sent. See what I'm saying? All right. I can verify my operation of my VLANs or my configuration of my VLANs by simply doing a show VLAN. All right, show VLAN. And I can see that ports are assigned to their particular VLANs. We've got our default VLAN, which can never be disabled. It can't be shut down. It can't be deleted. It can't even be renamed. All right. And I've got my management VLAN, and these are the ports that are active and so on. Is there any reason why a port might not show up in this list when I do a show VLAN? What types of ports don't show up in this list? Trunk ports. Because they're not a member of a VLAN. Trunk ports carry traffic for VLANs, but they're not actually a member of a VLAN. All right. I mean, the point of this class is not technically to teach you guys all about VLANs. We kind of make the assumption you know how VLANs work because you went through the CCNA class. If you're watching this video on YouTube, go check out the VLAN video and you can get some more details. All right. Or you guys can as well, of course. All right. The goal of this class is to make sure that you're implementing these technologies in a secure manner. Now, I said there were 3 things that are involved in creating VLANs. The first thing was to create the VLANs in the database. The second thing was to assign the VLANs to our ports. So what do you think the third thing is? Setting up your trunks, which is optional, right? You may not have trunks in your environment, but you do have to set up trunks. So I'm going to show you some of the best practice standards for configuring your trunk interfaces as well. 802.1q is the tagging method. People call this a trunking method, and they call trunks 802.1q trunks, but actually it's more aptly put that this is a tagging method because tagging occurs at the access port. When traffic enters a switch port in a VLAN, that's where the tag gets applied. So here's what a tag looks like. You've got your original frame, whether it's Ethernet 2 or 802.3 Ethernet, it doesn't matter. You got a destination MAC, a source MAC, your length or type or ether type field, right? Type field will be Ethernet 2 and the length would be 802.3 Ethernet. You got your payload and you got your frame check sequence, standard original Ethernet frame. As soon as, so I've got my switch port here, as soon as the data enters that port that's assigned to a VLAN, the only exception is VLAN 1. I think she thought I said Siri. Hey Siri, right? That happens to me all the time too. My phone thinks I'm talking to her. All right. So as soon as that frame enters the port, the switch is modifying that frame. It's inserting this 4-byte tag. That's a 4-byte tag. All right. Assuming you're using 802.1q. There is actually another tagging protocol. Cisco actually invented it. This whole concept of VLANs, the concept of tags and whatnot, that was invented by Cisco. So Cisco had another tagging protocol called ISL, Inter-Switch Link. Wasn't very well designed, but it did what it was supposed to do at the time. The main problem with ISL is that it adds 26 bytes of overhead. 26 bytes of overhead for an 18-byte frame. Pretty crazy, right? So most people will use .1q now. What is in this tag? A 2-byte ether type field, a 3-bit priority field, which is used for class of service. So that has nothing to do with VLANs. That priority field is simply to identify or to apply quality of service at layer 2. Then you have this F bit. The F stands for forget this bit, right? It's actually the CFI bit, the conical format identifier, or some people call it the token ring encapsulation flag. Obviously, given the fact that it's called a token ring encapsulation flag means that it's not used, all right? And then really the main piece of a tag is the VLAN ID. This is a 12-bit field, which means that we can go mathematically from 0 to 4095. That was supposed to be a 5. 4095. 2 to the power of 12 is 4096, but 0 is included. So mathematically, you can have up to 4096 VLANs. Now, VLAN 0 is not used, so there's 4095 VLANs, and VLAN 1 and VLAN 4094 are reserved for system functions, so you have some configurable ranges in between. All right? This is where the magic happens. That tag is what the switch reads to figure out how to forward that frame. Am I going to forward this across the VLAN? Am I going to send it across a trunk? Am I going to send it to a router? Whatever. All right? So the goal of implementing a VLAN hopping attack is to be able to manipulate that value. It's impossible for me to impose some sort of attack on another host in another VLAN unless my traffic gets routed to that VLAN. See what I'm saying? And usually when we send traffic up to layer 3, we're adding additional security. We have access control lists that filter traffic going from one network to the other. We have policies in place to secure that traffic flow. All right? So we're going to pause here. It's time for lunch.